All right, great. All right, thanks everyone for coming today. I'm Andrew, and this is my talk, Introduction to Native Extensions. If you'd like to follow along with the markdown source or any of the code, I did put it up on the internet. There's a QR code, so I'll give you a minute to scan that if you're interested. So today we're going to talk about what is a native extension. I'm going to give a motivating example, talk a bit about the benefits and drawbacks, show what Hello World looks like, talk a bit about some of the tooling that can support this, and then briefly talk about some alternatives and draw some conclusions. So what is a native extension? A native extension is binary machine code that you call from Python, Ruby, or JavaScript. So instead of having a function in Python, Ruby, or JavaScript that adds two numbers and prints them, you could ship the binary code 554889E548 and so on. Now, why might you, so this looks pretty inscrutable at first, but if we run it through a disassembler, we see this is a series of assembly language instructions, and it is loading one and one into some registers, and it's running add to add them together, and that's what's inside there. So why would you want to do that? Isn't it simpler to just ship Python code than try to compile this binary machine code and deal with that? And yes, it is, but let's write some Python code, and then let's compare it to a native extension running the same algorithm, and yeah, see how they compare. So the algorithm we're going to use is something called the sieve of Eratosthenes, which is for computing prime numbers. We want to know what are all the prime numbers from 2 up to some number, in this case 30. Well, 2 is prime because it's not a multiple of any smaller number. So we can just cross out all the even numbers. Everything divisible by 2, just forget about, not prime. Now, the next smallest number that's left, we know is prime, because if it wasn't, we would have crossed out as being a multiple of something smaller. So we have 3, we cross out the 3's. Next gives us 5, we cross out the multiples of 5. We end up with all the prime numbers. As Python code, it looks like this. It fits on one screen. There's a little bit of gymnastics here. We know even numbers are not going to be prime except for 2, so we can make this run twice as fast and use half the memory if we just skip all the even numbers up front. But the basic thing is we're just going to check for all the odd numbers from 3 up to n. If we already crossed off, skip it. Otherwise, we say this is prime. Then for all the multiples until we get to n, we just mark them as not prime, and then at the end we get the prime count. So when we run this, we see it's pretty fast, and there's 78,498 primes, less than a million, and it ran really quickly. It's simple code. What's the problem? Let's look at the native extension version. So this is C code, but it's pretty much the same thing. We see we're still doing for all the odd numbers from 3 up to n. If we already crossed it off, skip over, handle all the multiples, etc. So when I run this, it is building the native extension, and then we're running unit tests, and we have the test set up so we're running the same test suite with both the Python and the C version to make sure we get the same outputs on the same inputs. And then I'm running a tool called PyPerf, which runs the test code a bunch of times to increase the ability to draw statistically accurate conclusions about things. And when we come down to the bottom, the important thing is, so to compute those 78,000 primes less than a million for Python code, it took 120 milliseconds, plus or minus 3 milliseconds, but the C code took less than 3 milliseconds. So the C code was 40 times faster. 40 times is a big multiplier. It's the difference between waiting multiple minutes for an answer and waiting just a few seconds. So this is the motivating example. This is the speed up. That the benefits of using native extensions. The chief one is faster performance from being able to write machine code. And where this comes from is in the machine code, if you want to add 2 numbers, you just have the single assembly instruction, add the 2 numbers. In Python, if you trace through what the interpreter does, when it's trying to add 2 numbers, the interpreter ends up calling this function called PyNumberAdd, which takes in 2 generic abstract Python objects, and then it's checking, was the plus operator overloaded? And if it figures out, no, these are just regular Python numbers, then it can go into this long add function and start adding there. Now, Python supports arbitrary length integers. You can have a Python number with 100 digits. You don't have to do anything special. So the first one branch it hits somewhere in this process is it checks, are both numbers small enough that they like fit in a small area? And if they are, then it can specialize to just pulling them out and adding them directly, but it's looking at tag values, sign values, digits, etc. Pull stuff out, then it can add it. So all this abstraction is really nice in many cases. You get operator overloading. We don't have to care. We can add numbers and vectors. We can add matrices, but we're paying a heavy cost for that abstraction sometimes. And in the algorithm I just showed, that cost was a factor of being 40 times slower. So other benefits from native extensions, you have direct control over memory. So you can save memory, often saving CPU time as well. You can use real threads. You can reuse code written in other languages like C, C++, and Rust. And you can work directly with the internals of Python, Ruby, and JavaScript. So if there's something you're trying to do custom, there are handles to get in there and do that, which is great for experiments or advanced things. Drawbacks of using native extensions: crashes, incorrect results, memory leaks. C, C++ are much fiddlier to use than Python, Ruby, or JavaScript. And when you're taking something that's already a little touchy sometimes and adding in, hey, we've got to interact with the scripting language runtime, then there's just more chances for things to go wrong. Threads are great for speeding things up, but then you have to worry about synchronization, locking. You can get race conditions. Compiling and linking is another thing to worry about. Normally when you're running Python, Ruby, or JavaScript code, you just wrote your code, and figuring out all the details of how do you have to run this compiler correctly, what's the proper way to do linking on this platform, is something that whoever made Python, Ruby, or JavaScript that you're using, they had to figure that out. And then when you're working with the native extensions, all of a sudden that becomes your problem as well, which is sometimes not fun. Then you've got this trade-off. In practice, you need to kind of do both, but if you ship the source code, like here's my Python module, it comes with a C file. When you install it, the compiler needs to run. Sometimes users will get strange errors trying to install things they've never heard of, and they'll be upset. If you try to ship binaries, that mostly takes care of that problem, but then you're taking on the work of building and testing these binaries for all these platforms ahead of time. And then there's also overhead. I said that one of the benefits, like the big benefit of the native extension, is being able to have much better performance. So it might seem strange to start talking about overhead now, but there's, like I showed with the numbers, it's a lot of work to just get a number out of a Python number. So there's a lot of unpacking and packing and converting data formats that needs to happen. There's lost optimization opportunities. If you are using a Python, Ruby, or JavaScript that has a just-in-time compiler, that just-in-time compiler can't normally see through native code and optimize it. So you're losing some potential speedups. And yeah, and if you have, if you're not calling the native extension methods very frequently in your innermost loop, it's probably fine, but it's something to pay attention to and measure. And I did say you could work with the internals as a benefit, but having to only and always work with the internals of Python and Ruby and JavaScript is kind of a drawback. And then there's also security. Python, Ruby, JavaScript are generally considered memory safe. If you're working in those languages, you don't have to worry about accidental use after freeze, buffer overflows. But when you start pulling in your native extensions, if they're written in C or C++, then you do. The install time scripts for dependencies that trigger the compiler are scary. There have been a bunch of recent supply chain attacks, which are not fun at all. And if you ship the binary-only packages, malware can be hiding in them because the compiled version of the extension that you download from somewhere isn't necessarily matching the source code that it claims to be. All right, all that said, let's get to a hello world. This is hello world in a Python extension. We have just all the code. And so the key thing is we're doing the say hello method where we self and args, and we print hello world, and we return none. And when we run it, so it's just taking the C compiler, telling it to compile hello.c, output a file hello.so. Normally this would try to create a standalone program that runs main. When we pass -shared, we get a shared library, and then we just have to tell it where to find python.h and where to find the library. And then with that file generated, when we say import hello, hello.say hello, it says hello. And if we make a little change, hello world, let's change the period to let's change the exclamation mark to a period. If I rerun, quick and easy, we have an updated version of it. So I'm going to just show how this works at a high level and then come back and explain the code a little bit more for how this works. So in Python, when you say import hello, there's a bunch of import machinery that does a whole bunch of things, and some of those things are to look in a bunch of different directories for, is there a file called hello.py, or a file called hello.so, or on Windows, a hello.dll. And if it finds it, it opens it and calls pyinit underscore the name of the module, so pyinit hello or pyinit foo, and then that function will normally call py module def init, which passes in this chain of data structures that we've got a module definition, name hello, with this method table, say hello points at this particular method. So this is spelled different and more verbose, but it's basically the same as having a file called hello.py that just has say hello, print hello. When you create a file called hello.py, you're implicitly creating a module named hello just by virtue of the file name. And the list of module methods is implicit from all the def statements, but there is technically a list of module methods in there. So it's all the same concepts, they're just spelled differently. And the C code is just much more verbose, but also allows a lot more customization. So when we go back and look at that code that we ran earlier, we see here's the say hello method. It's referenced in this list of module methods. And the list of module methods is in this module definition. It says the module name is hello, and then we just pass that in. So that's how that works. Next thing up from hello world is accessing arguments, returning values, that sort of thing. So there's something called pyarg parse tuple that in this case pulls an object out of args, and then does the mapping lookups, and then adds things and returns an integer with this py build value. So this is what the native extension code looks like when it's not doing its own calculations, when it's trying to interact with Python values. And if we run this, it'll print 3 in there together. And when I warned about it being crashy, if I tell it to look for something else and I don't do a proper check on things here, if I try to run this, I get a segmentation fault, and I get the pop-up Python quit unexpectedly. So there are ways to code this more carefully. When I say warning error checking omitted, I really mean error checking omitted here. You can see the crash, but that's the general idea. Yes, Eddie. Yes. It's returning an array containing an object. Oh. Yeah, so you can build up arrays and tuples and possibly dictionaries as well in the output. So if you want to take things further, the doc you want to look for is something called Extending Python with C or C++. And it's part of the Python docs, and it just documents a bunch of these things. What is, if you want to get your keyword parameters, etc., we could, oh, sorry, okay, cool. And then, so that's more of a tutorial that gives you the basics and explains some of the concepts. There's also something called the reference manual, which goes into everything in detail. This is a very large document. You don't need to read it all unless you're doing a lot of very advanced things. But if you go into, for example, the object protocol, then it tells us, here's how to get look up the attribute on an object. So anything you can do in Python plus a few extra things you can do by calling the C API as well. So that's how Python native extensions work. So next up, what's it like for Ruby? It's very similar concepts, just spelled differently. Instead of including python.h, we include ruby.h. Instead of returning none, we return qnil. And instead of having a py object pointer for all the Python objects, it's just called value, all uppercase. And the initialization is a little simpler. Instead of having those statically defined things that we had with Python, we just say define module, and then we get something added to the global namespace, and then we can just define a module function. When we run it, compilation is pretty much the same, just a different extension. Ruby wants the library to be called .bundle, but we're passing in the include paths, the library path, building hello.c, and then when we require .hello and say do hello.say hello, it does stuff. And if we flip some characters and rerun, it's fast and easy to see. Here's the updated extension running the updated code. Great. Ruby also has documentation for this. You're looking for creating extension libraries for Ruby, and it's kind of the tutorial and the reference all in one. But here the, an overview of the concepts. And then further down somewhere, where was I looking for? What was I looking for? You know, if you want global variables, defining classes, this is the reference for how to do all of that. Now Node, hopefully this is looking familiar by now, but instead of using Python or Ruby header files, we're using the Node header. The core of the function is still the same, print hello world, but now we're returning null, and instead of a Py object pointer or a Ruby value, Node just uses something called an NAPI value. And the module initialization is a little different. Instead of defining a brand new module, the initialization code is passed in exports, and then you define a property descriptor on it, and then that property descriptor is what makes things work. And when we do the build, similar thing again, include the header files for Node. We're not actually doing a linker right now. It just says just don't try to do any linking right now. Just ignore all the undefined references. And the file is supposed to be called hello.node, but same deal. You know, hello world. Get your extension, and you can put whatever C code you want in there. So, yay. All right, and the docs for Node, it's called C and C++ add-ons with Node API, and it's got, you know, your functions for, excuse me, you know, if you want to get a value as an int 64, this is the function. If you want to create a promise, so there's, again, a little bit of a tutorial, and then here are all the functions to do all the things for integrating with your Node stuff, integrating your native code with the Node APIs. So I just have some hard-coded paths in the demos. I just said, you know, just get your Python headers from where I happen to have my Python headers on disk today. And that's not going to work if you're sending scripts that you want everyone to use. So there is tooling you should use for this. So for Ruby, there's the typical thing is xconf.rb. If you have a Ruby gem and you have xconf.rb in there, when you install the gem, Ruby will run it, and that helps do all the support stuff. And if you are a hacker, this is a fantastic place to put something to install malware, because anyone installing your gem will have this script run, and it can take over their computer and steal all their stuff. But when we run this, what ends up happening is, so running this ruby xconf.rb, it's nice that it's just a 2-line file. It generates this giant make file. The make file has a lot of generality for things that we're not doing in this case, but the important thing that it's doing is when Ruby is compiled, built, installed, it saves somewhere with that a memory of all the compiler flags it was built with. So that when you're building an extension, you should use the same compiler flags to build the extensions as Python, Ruby, or JavaScript itself was built with, so that things like stack layouts and so on are compatible. So what this ends up doing is compiling hello.o into, sorry, it ends up compiling hello.c into hello.o, and then linking that together to create hello.bundle, just like we did before, but with a bunch of extra arguments, some of which are probably useful, some of which don't really matter. But if I'd shown you this first, this would have looked super complicated, and hopefully seeing the simple example of like, oh no, you don't actually need all these things for hello world, hopefully that made this seem less overcomplicated. Python has something similar with setup tools in the pyproject.toml. You say, oh, by the way, you know, this project wants to use setup tools, and then I have an extension module called hello, and the source is hello.c. And then I found I had to fuss around with adding this cache keys and refresh package and so on to get like the tooling to actually rebuild the extension whenever I changed the code. But it did work, and normally it's very quiet, but I made it verbose so we could see it's doing same concept with when Python was built. It remembered what compiler flags it was built with, and it saves these to build with the extensions with, and then you get the same thing. Hello world comes out, and that was the wrong direction. And then once again, Node, generate your projects. Standard tool called node generate your projects. You say, I want to use node generate your projects in the package.json. In the install script, you say, do this rebuild. And once again, this is where if you were a hacker, you would say, put something to take over people's computers when they install the module here. And And then binding is a JSON file saying, okay, we want to build hello from hello.c. Then from JavaScript, we do hello.sayHello. And then exact same C code as before. It's just Yarn is usually pretty quiet about what it does, but I think I can do this. And then if we see what it was actually fully built with, it's once again the same deal with node remembers what compiler flags it was built with, and it has the tooling to supply those both proper paths to the argument, the headers and the libraries, and then all the arguments that will make you a more compatible native extension that shouldn't crash when you try to load or call or use it. So yeah, setup tools and make-file are at least 20 years old. There is some, yes?
Who knows what make-file is? Okay, not too bad. There's a text file that describes, here's a bunch of things you might want to build, and here's how to build.
Originally this was going to be a talk on Rust, and to fit in with the Python, Ruby, JavaScript theme, I needed to say, well, it's going to be, extensions for Python, Ruby, and JavaScript, but it turns out covering all of that doesn't leave any time to actually talk about Rust, so I'm not really going to explain the Rust, but this is what the talk was for. There is something called NAPI RS, which is Rust tooling for working with extensions, and this is what the source code looks like for this particular extension, and if I run it, Rust is slower to compile. This isn't exactly fair the way I'm showing it because I'm always doing clean builds in this particular scenario. But normally the incremental builds are fast, but when I run it, it's going to take a long time each time. But we say it's able to add 2 numbers, and this is something called a procedural macro. So when I talked about, you can't just do a plus b, you've got to do pi number add. Well, that's not actually the right example, but you've got to unpack values and so on. All those functions we saw in all that documentation, here's how you unpack stuff from Python, Ruby, or JavaScript into what you want to deal with. Here's how you repack it. So this procedural macro knows how to do all of that sort of automatically. So if I dump what it's doing behind the scenes, this is much messier than what you would get if you were doing it by hand, but the concepts are similar. That a function gets passed in an environment, and if you actually want to get the arguments, you have to do something saying, okay, call back to node, tell me what my argument 0 was, and it comes as an NAPI value. And if you want it as a 32-bit integer, then you have to call from NAPI value. You have to do all that, but with this way of writing the native extensions with the newer generation Rust tooling, you can mostly ignore all of that. You can just say, oh no, I just have a function that takes in 2 numbers and adds them, and just put this on here, and it does all the work of making that fit into the node system. And I said earlier that a benefit of working with native extensions was you can leverage existing code in C, C++, Rust, etc. And so with this, it's, if there's some Rust library that does something useful and you want to use it from Python, Ruby, or JavaScript, with this NAPI RS, the procedural macro, if the input text, we can just say it's a vector of string and the return value is a result of string. We can call this text processing library and have it handle all the details behind the scenes of how do I get a JavaScript list here turned into a Rust list. And when we run it, and again, it's a little bit unfair to show the compile times for Rust because this is the clean build, but do remember the basic example did run in like 1/3 of a second, and this takes like 7 seconds, but now it says, hello from NAPI RS, and if I, say hello Meetup instead, so normally the extension would already be compiled and this would be instant. You wouldn't have to recompile it, but if we do recompile it, then there it says hello Meetup in the cool old-fashioned font for people who know what makefiles are. All right, and then so just some alternatives. if you don't care about writing your own code in some other language, if you just want to use existing libraries, something called FFI lets you just load the libraries and do calls, and there's some stuff to figure out, but it's a related technology that avoids some of the stuff with native extensions. Swig, the scalable wrapper interface generator, does build native extensions for you, but it'll write out a bunch of the code, sort of like what that procedural macro was doing. And then you should know about WebAssembly, or WASM. It's a portable assembly language, so if you want performance that's better than what Python, Ruby, or JavaScript will give you, but you don't quite want to go to the level of having to compile a bunch of different native files for a bunch of different platforms, WASM is a nice in-between where you compile it once to a WASM binary file, and then you're able to use that in the browser automatically without any libraries, to use it in Node on the server, to use it in Python or Ruby as well. And so it's a nice way of doing a portable thing with better performance. The only issue is it is sandboxed. So if the reason you were going with a native extension was that you wanted to deal with files, network I/O, talking to hardware, WASM's not a good fit. But you know, the Civ example I showed earlier, if we had some code to compute prime numbers and we wanted it faster than Python, Ruby, or JavaScript, but we didn't need it to be the fastest possible, then WASM would be great because it would simplify a lot of the complexity of building stuff. And then don't forget about remote procedure calls, RPC, sometimes just called services. But if you've got code in C, C++, something else that you want to call from Python, Ruby, or JavaScript, you just add a server component in that code and then just make the calls from the socket. The overhead for this can be surprisingly small, and you don't have to deal with any of the multi-language build stuff. And tools like Docker Compose have made it a lot easier and more common to just have different binaries together that make up a system and be managed together. So conclusions, it's relatively straightforward to start using native code to expand and speed up Python, Ruby, or JavaScript code. You saw the hello world. Most of the tooling stuff was relatively straightforward to get working. General approach is the same across scripting languages. Like, things were spelled differently, but it was all the same concepts across all the languages. It requires fiddly work to convert data formats, even for integers. There's overhead for the frequent calls, so something to be aware of. But Rust is getting popular for writing the extensions, which avoids some of the issues with memory unsafety, that sort of thing. And also newer generations of tooling, just when someone's newer generations of toolings are trying to automate things more. So just by using some of the Rust stuff, you are getting things where they fixed things that have been around for 20 years that people have decided, no, it's not worth the change because everyone would have to relearn it. So thank you so much for watching my talk. Yeah, I'd like to, any questions? Yes.
Let's say there's a large company with lines of legacy.
Mhm.
This type of approach used more per se in that circumstance to get new functionality like functions, call them into the C, or is it to say start writing new programs in Python or whatever, and then call the legacy code as opposed to like rewriting the legacy code?
Yeah, I think it would be the latter. Like if you have a big C library that does some simulation or something, and then you're, if you had an old desktop app and you're saying, now we want to move it to more of a web thing, and we want to just use Python to serve up the web pages, but still be able to perform these computations, that's where you would wrap the existing C or C+ code and then use Python as sort of the driver to interact, to give you just a friendlier language to interact with that functionality.